Welcome to Chemistry 312. We'll finish up Chapter 17. So we've just talked about ortho and para directors. Now there are a class called deactivating meta directors. So they do two things. Not only do they force uh, a substitution at the meta position, but they also deactivate the ring so to make the ring actually less reactive. They are less reactive than benzene, and thus they need harsher conditions. And even though they deactivate it, they will give meta. So these guys are electrophiles. They're substituents with electron withdrawing capabilities. It will that while it won't deactivate the meta position, it will deactivate the ortho and para. So you're forced to get one. So like I'm gonna put like the simplest one would be nitro. So NO2 because it's positive nitrogen. So if I put the electrophile here, look at our three structures. Wish I could. Let's see. Okay, I'm not sure I can copy. Wish I could, but make it a little bit easier. But okay. Draw three possibilities. Well, I think you'll get the idea just by one. The idea here, this is nitrogen. The two of them are perfectly two of these structures are perfectly reasonable. One of them puts a positive charge adjacent to electron withdrawing nitrogen. Thus, it's going to deactivate that position. The same way with doing this with a para position. That's plus EH. This structure is going to be deactivated. And we can have a plus there, or there. Same thing, we can have plus there, or there. And this one is our deactivator. This one is our deactivator. Well, with a meta, the meta EH, we could put a plus here, here, or here. And in no cases will that positive charge be attached to the electron withdrawing substituent. So while none of them are particularly stable, none of them are actively destabilized. And so this energy of the electron withdrawing will make it the energy higher for all compounds, but especially for ortho para in particular. So meta directors include, but are not limited to, NO2, SO3H, so our sulfates, cyano. Remember when we did the Diels-Alder, cyano was an electron withdrawing group. Aldehydes of all type, ketones. Esters and acids. And other compounds with positive charges, like alkyl, well, that would be ammonium complexes. So anyone with an actively positive charge. Now, there's one other class that are deactivators, but act as orthopara directors. So right now we have nitro, sulfates, cyano, any type of carbonyl compounds, and positively charged amines. Well, the halogens will act as orthopara directors, but they will be deactivating because so X is a deactivate, right? But they're going to act as OP directors because X is strongly, halogens are all strongly electronegative. So they're going to be E withdrawers. And that's going to make them sigma acceptors. Sigma acceptor. But they also have lone pairs to donate. So that's going to make them what's called pi donors. They're going to accept and pull electron density through the sigma bond, but they can push it back through a pi bond. So while the energy may go up with them, they will stabilize the ortho and para position. So when we have multiple substituents on here, we must take them all into account. However, certain ones count more. And the big thing is activators. Activators are stronger, are greater than deactivators. So if you have an activator and a deactivator on there, you're going to take the activators thing first. So we're going to count first strong OP, such as OR or NR. Then you might consider moderate orthopara, such as halogens, alkyls, and then maybe halogens, because they're slightly deactivators. And then finally, meta. As I said, if there's two opposing groups, the stronger group predominates. So, and so we'll look at some more reactions here, some more different electrophiles, because it's not always just good to add a halogen, a nitro, or a halogen and nitro, or like say sulfate. But as I said, let's give an example of this before I move on. I have there, these guys are not actively opposing. Methyl group is a ortho para director, so they will want to give there and there. Nitro is a meta director, so it wants to give there and there. So next group I put on, those guys work together. However, if I had a structure that like this, ortho pair wants ortho there and there, and nitro wants it there. So which one would we get? the X's or the pluses. We're going to get the X's. However, 1, 2, 3 substitution is highly sterically hindered. So if you have a choice, you're going to put one here or here. So you could have like 1, 2, 4 substitution. Because the alkyl group beats up meta directory any day. Okay, so the next class of reactions is called Freidel-Craft's alkylation. So Freidel-Craft, we're going to abbreviate this later on as AC. Freidel-Crafts, named after the two scientists that discovered this. Alkylation. Alkylation. Now, it's essentially, we're going to use a Lewis acid to add a R group to a phenyl. It's a convenient way to extend the chain length of a benzene ring. You start your benzene, you add something onto it, and keep working. The basic reaction is you take a benzene or some sort of or a substitute thing, you add a halogenated alkyl, and we use one of our Lewis acid catalysts. It could be aluminum chloride, could be iron tribromide, or it could be iron trichloride. Any of those guys will work. And the net reaction is and HX. Why does it not matter which catalyst and what's attached to those catalysts? Well, you're making the halogen is binding onto there, and the R plus is much more stable than the X plus. So R is the preferential electrophile. And so it doesn't really matter. It doesn't matter which halogen you use. Now, the beautiful thing is this can work with primary. This could be a primary, a secondary, or a tertiary alkyl halide. Now, it depends on the catalyst may depend on. The actual mechanism kind of depends on the secondary or tertiary. But so we'll look at that. So with secondary and tertiary, the mechanism is a two-step. So let's look at a tertiary, terbutyl chloride. So we do that. We add aluminum chloride. This was secondary and tertiary. Similar reaction. You form the carbocation, aluminum chloride, and then at that point, the benzene will attack. Yada, yada. With primary, it has to be concerted mechanism because the carbocations are not particularly stable. So basically, we have a methyl. It's kind of like a SN2. Methyl, we have. This is already being stabilized by the aluminum chloride. And so it's attacking there, kicking that off, which then goes directly into there. Now, there's other sources we can actually do with certain cases, and like add an alkene through the pronation of an alkene, hydrofluoric acid. Let's see. So let me show a couple other ways to add alkenes. The pronation of an alkene. So we have this group R. We use HF. Now, while this is not necessarily stable, we make this electrophile, an F minus. And at this point, we can add in the benzene. And HF acts as a catalyst. There's our electrophile plus our benzene, yada, yada, yada. We now have a new compound. We can also use alcohols and BF3. Alcohols and BF3, but the BF3 is a reagent. It's not a catalyst. So we can use R, OH, in the presence of BF3. That's a really strong Lewis acid. You're going to form R plus and HOBF3 minus. There's our electrophile. Now the limitations are these. This really only works with benzene, activated derivatives, and halobenzenes. So these things aren't net. The Freidel-Craft acylation. So let me clear this off so I can. FC alk. It's like works with benzene, activated, and halo. So what does that mean? If I want to add a alkyl group, I have to either start from benzene and add it first, or activate it with something, or even halogenate it with something. I cannot do this. I cannot add plus R plus, will not work. That will not work. Remember, activated, so this will. But that will not. So only works with benzene, activated, and halobenzenes. So we got to think about it, because it's R plus is maybe not as good as other things. Now another consideration. That's just the first for FC alkyl. Oh, the first. Some of the most important, that it won't work that way. 2, the alkyl cation, the R plus, is prone to rearrangements. Same thing we got to worry about in SN1s and E1s. Prone to rearrangement. So we typically use T-butyl or isopropyl or ethyl groups. to avoid this. To avoid. And 3. That alkyl addition further activates and thus could causes multiple additions. So how do you get away from multiple additions? We use excess reagent, excess benzene. So if I have, so looking at that one again, if I have this plus Rx excess, we're going to get something that looks like this. R. You might have R. Then it gets a little messy. Or R right there. So you might get more than one addition. But if you add this benzene in excess, you're only going to get one addition. Unreacted. So you're going to get lower yields, but you can stop it from going too far. Okay. Now, continue going. It's just one class. There's another thing we can do. Is that this is called Freidel-Craft's acylation. Acylation. That instead of adding an R group, we're going to add a carbonyl group. Carbonyl. And we can use this with either acyl chlorides or acid chlorides. So it's very similar. We're going to have, say, R, C double bond O, OH. And we're going to use, say, thionyl chloride. And it's going to form, we're going to learn about these classes later semester, but forms a very reactive acid chloride. ACl. And then this. If it's already in an acid chloride, we're good. We're golden. But if it's not in an acid chloride, we have to make it an acid chloride first. We use our Lewis acid, say aluminum trichloride, water. Bada boom, bada bing. We have a deactivated carbonyl onto there, an HCl. So same general process. How do we form the electrophile? We're going to have RCO. Cl. The only reason I'm showing this real quick is because this electrophile is stabilized. Stabilized to form, we have R, C, double bond O, plus, but it's also resonance stabilized with our C triple bond O plus there. And so that's your electrophile that gets attacked by the benzene ring. And we can deprotonate that to reform the catalyst. Now the water is added to stop the aluminum trichloride from complexing with the acyl benzene. We're going to stop that from reacting with the benzene once it's already added. Now, this will typically add in the pair position in orthopara due to its bulky, due to steric hindrance. So if I have, just say that, and I'm going to do RC double bond O Cl, we're going to typically get para, just because it's a steric hindrance here and there. Now, you may say, oh, that's well and good, but that's not very useful in all situations. However, just like we did with the nitro group, we can do something called the Clemensin Reduction. We can add this and then reduce it down into something we maybe want. Clemensin Reduction turns OR into CH2R. It's going to reduce this down. We're going to use zinc mercury catalyst. Zinc mercury. It's the metal catalyst, and in aqueous HCl, so it doesn't need to be super concentrated, but and you result down with a CH2R. Now this is useful to add an alkyl group. The Freidel-Craft's alkylation couldn't over add, but deactivators will tend to stop the reaction in its track. So you add a deactivator, remove the excess reagent, remove this, separate it, and then reduce it in a separate step, thus preventing over addition of the alkyl group. So that is one way you can add an acyl group without over adding. It's a way you can add an acyl group without worrying about its rearrangement because it's stuck. You're limited with the CH2 at that point. Now, there's a couple other reactions I'll show you. Gatterman-Koch formulation, probably not as useful, but it's interesting nonetheless. If you can't already tell, that's German for, but it's just adds a formyl chloride group. A formyl chloride. It's so we're going to add carbonyl as a gas, HCl, and the presence of aluminum trichloride and copper chloride, we form this formyl group, HCO plus, which is our electrophile. Then we add in our benzene. And you're going to add formyl. Otherwise, the formyl is not really stable otherwise. So you need that. Another class. works similar, but we've done electrophilic aromatic substitution. So of course there should be some nucleophilic aromatic substitution. Works in a similar sub. NAS instead of EAS. The nucleophiles will replace a halide or other leaving group. Now, this can't be SN2 or can't be SN1. So it has to have a completely different mechanism. Can't be SN2 because there's no backside attack. If it tried to backside attack from this ring, you're coming from the center of that ring. It can't be SN1 because it needs a strong nucleophile, and the nucleophile is involved in the rate determining step. So we can't just drop off the halogen. So we need an electron withdrawing group. Group will activate the ring. Activates ring. So this is the exact opposite with the electrophilic aromatic substitution. It activates the ring. Because the transition state has a negative charge in ring. So electron withdrawing group puts the negative charge on the ring, and thus we're more likely to electron withdrawing group removes some of that charge and stabilizes this. So for example, addition/elimination of chloride by replace chloride with alcohol. So let's put some groups on here. So we have a nitro group. These are going to would have deactivated it in the normal situation, but this situation, it's going to activate it. So NaOH, 100 degrees, 2 equivalents. The first things we're going to do, we're going to add this, add an O minus, and then finally we're going to protonate this, and bada boom, bada bing, we have a phenyl group. Nitrophenol. Now, important thing is, you could have, instead of those nitro groups, sulfates. Those sulfates, remember, we can remove with the proper amount of heat. Proper amount of heat, you can punch them back off, and a way to make a phenol out of, say, chloral. But so let's look at that. Let's look at that, putting the ring in. What's actually happening? So we have chlorine. And we'll just put N+. I'm going to just draw in one of these nitro groups. So the first step is the OH minus is going to go, bam, kick the lone pair down there. This is our RDS, rate determining step. The nucleophile is in the rate determining step. So we have these 3 resonance structures, Cl, OH, negative, boom, boom, NO2, NO2. This particular case, 2 of these guys are going to be activated. So, negative charge here. So that one's activated. ClOH. And that one. Oh. Okay, well, I guess let's see if I can erase this. And let's see. Just put that there. O minus plus. So the two structures on the right are activated. They're more stabilized. From at that point, we can. Why are they stabilized? Because we can do a resonance structure of this lone pair swinging down, this swinging up, kicking that up, and moving that over. This nitrogen acts as a pi acceptor and accept the electron density into that nitrogen through the pi bond, thus stabilizing this structure. The next step, fast. This negative charge goes there, it kicks off the chlorine. And so that we have our next structure, which is our NO2, OH minus, NO2. The next thing is unavoidable because this is even faster and more preferential than the previous step. We depronate the phenol because phenol is an acid, all things considered. We can't avoid this. If we tried to add only one equivalent of base, you're going to only get 50% yield at best because as soon as we make the phenol, we're going to depronate it because it's much rather act as a base on itself than it would act as an electrophile. Sorry, act as a nucleophile and attack the ring. So we need to add those two equivalents of base. We can pronate it later when we no longer have any base. But if we pronate it too early, we're going to stop the reaction. So in this case, electron withdrawing will activate the ortho and para positions. It's very contradictory from what we learned, but it's the same. Let's see. Very contradictory, but if you think about the logic behind it, it makes perfect sense. Electron withdrawing deactivated for carbocations. Electron withdrawing activates for carboanions for the exact same reason. Now, an unactivated benzene will undergo a different mechanism requiring stronger bases or harsher conditions. Now, there's some very interesting here, Benzyne mechanism that requires very strong bases. So let's look at this. So bromine, H. Look at this. So very strong base. Instead of using OH, we have to use NH2 in the place of ammonia and negative 33 degrees. We got to keep this from overreacting. So what's going to happen? You're going to deprotonate adjacent to the halogen. I'm going to remove that proton. This lone pair is going to swing up, kick that off, and we're going to form what's called a benzyne. So benzyne is when you have a triple bond within this benzene ring. Now this NH2, because we excess NH2 minus, will go attack one of these two positions, reforming the negative, and then can protonate it with NH3. So you're going to get, in this case, neither side of that alkene is favored. So you're going to get 50%, in this case, para substituted, and 50% meta-substituted. You can't avoid it because neither of those benzene is particularly more reactive. 50-50. Now, note it needs a stronger base, but in this case, no electron withdrawing group is needed there. Now it's possible to also do aromatic substitutions with organometallics. So just a quick thing, organocuprate. Remember, we could do this. Rx plus 2 equivalents of lithium. It forms R, Li, and LiX. Then we can use 2 equivalents of the RLi and copper iodide to form our R2CuLi and LiX, or LiI. And then in the presence of a different guy, R prime X, we can snap these two together to form R prime. And of course, one that didn't react. You can attach anything, any alkyl, vinyl, or aryl halide to any alkyl, vinyl, or aryl halide. So you could easily snap together RCl. Doing that, it would of course take 3 equivalents because you have to do the first reaction twice to make that, and you'd only get 3 of these would go down to 1 of these. But you could do it. Let's snap those two together. You could put a vinyl group onto there if you want to extend the conjugation system. Now, particularly, here's one that works similar called the Hack reaction. The Hack. We can use this with any aryl or vinyl. So Rx. This is another good reason to add these halogens onto here. Any phenyl or vinyl. And we can add a vinyl group onto there without going through all those same steps. Palladium and triethyl ammonium as the solvent, and it just snaps that on there. And that forms triethyl ammonium instead of triethylamine. What? Triethyl ammonium chloride. Ammonium halide. We could also do something called the Suzuki coupling. Suzuki coupling. It's kind of a neat one where same thing. The same thing, any phenyl or vinyl group in the presence of either of these two reagents, either R prime B R prime boron trihydroxide or R prime boron alkoxide, dialkoxide. We're going to add on in the presence of lead and sodium hydroxide. We can just snap together 2 groups. So to form eventually BOH 3 and NaX. The mechanism involves some oxidation and going through essentially an addition to the metal. So basically, first thing we're going to do, palladium 0 acts as an oxidizing agent, and we do what's called an oxidative addition to the metal to go to palladium 2. And then from there, with the boron does an exchange, R, UOH 3. It captures the halide and essentially puts the other group onto the metal. Still, now it's like BOH 3 with the halogen. And then it can undergo what's called a reductive elimination to reform the catalyst. Palladium 0, and these guys get snapped together. Oxidative addition and reductive elimination are very common reactions in inorganic chemistry. It's essentially understanding the metals. What are they doing? And they're just by oxidatively adding to things and then reductively eliminating back off, we can exchange those. Now we have a few more important reactions to go through. These are really short ones. They are not classified under the nucleophilic aromatic substitution or the oxidate or the electrophilic, but they're useful because they modify your side chain. So we got to think about this. We got to think about, we put on a side chain and what can we do to change it? What can we do to change it? So we can use permanganate to oxidize the carbons in the side chain. So any phenyl R, the presence of permanganate, KMnO4, and OH, it doesn't matter the chain length. Here's the important thing. It doesn't matter the chain length. The result is the same. You're going to kick the shit out of your chain, and it's going to fully oxidize it to carbonic acid or carbonate. And then you're going to pronate that to carbonic acid. So this oxidizes everything. The only thing that it doesn't work on is NO2, X, already carbonates, and SO3H, sulfonates, are immune. So these guys will not react. NH2 will go all the way to NO2. Let's look at other groups. Let's see. Acyl groups will get fully oxidized. So, but any kind of carbon chain or reduced nitrogen chain will completely react all the way up. So that's one thing you got to look at for. The aromatic group is immune, but so this is one way to fully oxidize something down. You put a chain on, you oxidize it there. We can look at a side chain halogenation. So once we've added our group, we can change the side chain. So the basic idea here is R, and we're going to use chlorine and light. It's going to go through radical. We're going to attack. So I'm going to attack here and form the product. chloride. Let's see. We're going to attack alpha to the. I don't think it's going to form attack on the second group. It's too reactive. It cannot attack on the chain. I mean, it can't attack on the aromatic very easily. And I don't think it's going to have multiple additions. Look this up. I trying to find trying to remind my notes, but I don't think it's going to add multiple times. I don't think this is very unlikely. And I don't think that's very likely, and I don't think it's going to add to the second carbon. I think that we can do the same thing with bromine. Okay. Actually, no, I might be mistaken. Chlorine may be overly reactive, so it may form some amounts of that and some amounts of that. It's very, very, very reactive. So a much better halogen to add would be bromine. Bromine, same mechanism, same mechanism, using light, forming radicals and all that jazz. You're going to form mostly this and trace amounts of secondary addition. So we don't have to worry so much about the byproducts. Right, trace. And we could also look at the final thing we'll go over is the nucleophilic substitution to the benzylic position. Last thing. So this works just a SN1 mechanism. So SN1. And that this halogen can easily fall off because this carbocation is so freaking stable. That plus right there is stabilized by these resonance structures. Boom. Put a plus right there. Shoot. Plus right there. Plus right there. So we have these three resonance structures in addition to the main structure you would expect. And so it's as stable, if not more stable, than a tertiary carbocation. So at that point, the nucleophile can attack. Bam. And you add there. It's not going to necessarily add to the ring because this structure is far more stable. But it is stabilized. SN2 mechanism would use the p orbital of a benzylic atom. So SN1 just goes like that. So it's very possible to add SN2 and SN1 onto the benzylic position. Okay, so that is the end of the video. This is caught up with all of the old videos. This is after this point, Bethel would have shut down for a couple weeks to get everything back. So this is where I'd start the normal lecture notes. I've now completely caught up. Thank you for your time. I hope these will be helpful.